What does a child's spinning gyroscope have to do with flying an airplane? More than you might imagine. Remember how when you were a kid you'd spin a gyro and it would stand upright for almost as long as it had motion? You probably didn't know it then, but it was exhibiting a property common to all spinning discs, a property the engineers call rigidity in space. As the name implies, the disc wants to remain as it is. A gyro is a spinning disc whose axis is mounted in a frame that allows it to move freely in several directions. As we mentioned, the gyro wants to remain as it is. And you'll soon discover that some of the instruments in your Skyhawk use gyroscopes that work on the principle of rigidity in space. Now, precession is another property of a spinning disc. If you push on the axis of your gyro, it resists the push, and the force you applied actually moves in a direction 90 degrees from where you were pushing. In the same way, when you pitch your Skyhawk's nose down, it wants to go to the left because of the propeller's gyroscopic effect. Both of these are examples of gyroscopic precession. Precession is what lets you turn your bicycle by leaning in the direction you want to go when you're riding with no hands. Precession is predictable, and you have a gyroscopic instrument in your Skyhawk that uses the principle. When it's used intentionally, precession can work to your advantage, but it can also work against you. Because of the friction in bearings and other reasons, precession sometimes shows up where it's not wanted. For instance, when it causes gyros to drift instead of remaining rigid in space. In this case, the airplane designers offer a couple of choices. They either build in a correction for it over time, or they provide you a means to adjust them. So now that you understand the principles that operate gyroscopic flight instruments, you'll be able to gain confidence in them. The three instruments that employ gyroscopic properties are the attitude indicator, the heading indicator, and the turn coordinator. Before we discuss the instruments, though, let's talk about what powers them. There are two different sources of power for the gyro instruments in your Skyhawk. They are the engine-driven vacuum pumps and electricity. The reason for this duplication is simple. If one power source fails, the remaining gyro will furnish enough information to, say, allow an instrument pilot to successfully complete a flight through clouds. Conveniently, on your Skyhawk, the power source for each gyro instrument is displayed on the dial face, so that in times of adversity, you'll know what makes each tick. As you can see, the heading indicator is powered by vacuum. The attitude indicator is also powered by vacuum, and the turn coordinator is powered by electricity. The vacuum system uses two engine-driven vacuum pumps working together. The pumps suck air from the instrument case, creating a vacuum, while filtered cabin air then rushes into the case through a nozzle. The nozzle directs the inrushing air at the edge of a gyro disc that has little buckets in it, much like an old-fashioned water wheel. Sucking the air out of the instrument case may seem a bit backward when, after all, the intention is to make the gyro disc spin by squirting air at its edge. The reason is that it's easier to filter the dust from the cabin air than it is to filter the oil and metal residue from the air inside the pumps. Now, if one of the pumps fails, the remaining one can maintain sufficient vacuum to operate the system. In fact, you might not even know there had been a failure, except that an amber annunciator light will illuminate on the panel to tell you which pump has failed. The vacuum gauge here on the left side of the instrument panel measures the health of the vacuum system. Its normal operating range is from 4.5 to 5.5 inches of mercury at sea level, or in the green area. If the vacuum is too high, there is a chance that the instruments could be damaged because of disc overspeed. If, however, the vacuum is too low, the disc may turn too slowly to maintain the gyroscopic properties needed for proper operation. In fact, monitoring the suction gauge is part of your pre-takeoff checklist during the engine run-up at 1800 RPM. The indication should be well within the 4.5 to 5.5 limits at that RPM. But when your engine is idling, the vacuum gauge may indicate as low as 3 inches of mercury. So if you operate the engine at idle for a prolonged period, you should check your heading indicator against your compass to ensure it's operating properly. Now, as we mentioned, the turn coordinator is the only gyroscopic instrument that uses electrical power. The gyroscope in this case is the rotor of a small electric motor. If the entire electrical system were close to failure, volts would light up on the annunciator panel. However, if you notice a red failure flag on the instrument face, it would indicate a failure of the instrument itself. And now that you know how the gyro instruments are powered, you should be able to recognize potential problems and how to avoid them.